Alrighty, so we're looking at some LTSpice, and I've got a example here already, and this is a current source to test a transimpedance amplifier for some sort of optoelectronic detector application. So we have a network analyzer which is on the left, and it's got two inputs, which is input R at the top, which is R11, and input A, which is R7. And the job of the network analyzer is to plot the voltage on R7, which is node A, divided by the voltage on input R, which is R11, and we call that node R. And the whole system is driven, of course, by V4. R5 is the output impedance of the network analyzer source, R11 is the input impedance of the network input R, and R7 is the input impedance of the network analyzer input A. R9, R8 and R10 are a power splitter, and that impedance matches. I hate Windows. Couldn't give a damn. Leave me alone. Right, yes, power splitter. Impedance matches the R11, R6 and R5 effectively, so there are no reflections back and forth along the B and C cables. Obviously the V4 and R5 are in the network analyzer, and then the R8, R9 and R10 are somewhere on a little circuit board, and then R6, U1, R1, R2, R3, J1 and R4, C2, C1 and C3 are all on the circuit board that the student has decided to make, and R7 is in the network analyzer, so is R11. So the circuit itself is not particularly important. The purpose of the video is in fact to deal with some layout techniques for high speed, or at least modest speed circuit boards. The job of the circuit also is not very critical, but we should know at least that the op-amp is switching on the JFET in such a way that a controlled current flows in R3 and in R1. And the controlled current in R3 are designed to be, I can't remember what, let me run it and see. It's 1 or 2 milliamps effectively. So I will just put a new command down by clicking here for the operating point is op, and if I click the running person, sure enough I don't get the operating point. Let me just comment out the AC analysis. Come back to that in a bit. So I get a list, which is very unhelpful. It gives me all the nodes and everything, but I'd much rather look at on the diagram. So I've got some notes here that tell me what's going on, and you can put those down with the right click, and then draft, op data label. I can put it down. If you put it somewhere that's not connected to anything, it doesn't know what to do. If you want to put it somewhere, just press F7 then to get the move up. If you put it on a node, it will tell you the voltage on the node. So I try to put one somewhere where there's something useful. There, it's going to be minus 250 millivolt, and sure enough that's what this DC source is providing. F5 for delete, and then a right click to get rid of the delete. Also escape works fine. So these ones I didn't put it down anywhere. What I've done here is I right clicked it when it was new, and I said I wanted the drain current, I for the current, D for the drain, and in J1, or J1 is the 2N3819, which is our N channel UHF JFET. Same with this, I've done VG minus VS, so this is the gate to source voltage of the JFET, and sure enough, if you have 0 volt on the gate with respect to the source, then the saturation current flows in the JFET, because you have to turn the JFET off rather than turning it on like you do with an enhancement mode MOSFET or a bipolar junction transistor. So we are expecting to have to make the gate somewhat negative with respect to the source to control the flow of current from the plus 15 supply provided down here, through the 50 ohm, which is my effectively my output resistance, through the drain and the source into the R3, which is my current setting resistor effectively. And all I'm really doing is say, well, I've got minus 0.25 volts here. This is a inverting amplifier, and this is ground as far as DC is concerned. I can prove that quite quickly. I just copy this one, pop it down there, right click, and I can use the dollar, and that will be whatever the current node is. So I go back now, it just shows dollar, but the dollar alias is to the node 5, which is the node on here. I can see that if I look in the bottom left, if I look down here, you can see it's VN005. So as far as the DC is concerned, this is grounded. It is equivalent to this situation. That was G for ground, F3 for a wire, and then a right click to get rid of it. That's effectively what this source thinks of the circuit. But there we go. Get rid of that as well, F5 there. I can probably get rid of that too. So it's doing everything in its power, the op-amp, using its big open loop gain to try and make its output go to, the feedback node here go to minus 250 millivolt. Sorry, plus 250 millivolt, because it's inverting. So if I was to put a data label there, right click just then, just the background, and then put the data label, put it there. That's very ugly indeed. Move it with F7 to just here, F3 for a wire, click click, done. 250 millivolts. So yep, it's got a gain of 1 because I've got R1 and R2 equal. Gain of the circuit is minus RF over Rin, or minus R1 over R2 in this case. So yeah, it's working, we think. And to make this happen, the op-amp has to adjust its output in order to switch on, or rather switch off, the JFET by just the right amount to cause just the right current to flow in R3, to cause just the right voltage across R3 to make the 250 millivolt here. And it's using its big open loop gain to do that. As it happens, there must be some voltage across R1 as well. Now, if I said to you this point is 0, then it's a pretty good chance this point is 0 as well, because we've got the negative feedback and we've got the large open loop gain. So if you were in EE118, you know that its op-amp is doing everything it can to push the two inputs together. So if I was to get a data label, I would just copy this one. F6 for copy. I missed. I missed. 819.3262 nanovolts. Not very much. E minus 9, so that's less than 1 microvolt. So basically it's ground, more or less. Virtual Earth, anyway. So this node pretty much ground, so I've got 250 millivolts here, so I've got 2.5 milliamps in this pathway, because I've got 250 millivolt divided by 100 ohm. And I've got 2.5 milliamps, pardon me, in this pathway, because I've got 250 millivolts across here. If I ask for copy this one, what node is this? That's node S. Oh yeah, because I labelled it. If you need to label your nodes, by the way, F4. I could, if I wanted to, put an input node just here. If you label up your nodes, you can then demand V open brackets input close brackets. If you do that though, you must rerun the simulation. So for this one I can ask it for VS minus VN06. There's a slight difference in the last couple of units because we know that this node here is not really exactly ground. So if I want the current in this pathway, I can ask for that as well. That's a bit ugly, let me move it down a bit. So we need IR1. There we go, and that tallies up quite nicely because I already measured 5 milliamps more or less in R4. and the current flows through R4, flows through J1. There's no gate current, or very small gate current, because the gate to source junction is reverse biased in the JFET. And then we have the drain current and the source current equal to each other. Drain is this one, by the way. And then the current reaches this node and it splits off in this equally in these two directions because it sees the same resistance to ground in each direction, more or less. So that's the overall setup. C1, C2, C3. As far as SPICE is concerned, simulator, there is no need for me to do this. I'm only doing it here because it's commonly done when you actually build the circuit. If you need a AC coupled system which has got good low frequency response and has good high frequency response, you need more than one kind of capacitor. The 220 microfarad capacitor will be electrolytic. It will be, if you were in the 118 lecture 1, a spiral of 2 bits of foil, probably made from aluminium or something like that, with something which is akin to peanut butter in between. It's not really peanut butter, and this is it's got a reasonably high permittivity, and we make the capacitor by the usual method. It's E naught ER, or epsilon naught, sorry, epsilon R, A upon D, where A is the cross-sectional area of the plate and D is the distance between the two. And epsilon R is the relative permittivity of the dielectric medium, which is the, in quotes, peanut butter. The trouble with the electrolytic capacitor like that is they're spiral shaped, and they're usually physically quite large, especially if you want to withstand a reasonable voltage. 60 volts or so is quite common. So because they're spiral shaped, you get inductance effectively, and as the frequency goes up, the capacitor starts to look less and less like a capacitor, and eventually it starts to look more and more like inductor. And if you want high frequency signals to travel through inductors, then you're going to struggle because the impedance of the inductor goes up with frequency. So we have to do something to try and make a better high frequency capacitor and low frequency capacitor. So C2 will be electrolytic. That will give us the low frequency performance because it's got a very high capacitance, quite high capacitance value. And then C1 and C3 will be, C1 is probably going to be ceramic. It could be polyester or polypropylene or one of the plastics. C3 will almost certainly be a ceramic capacitor, which is metal and ceramic between the two in some sort of interdigitated structure. It's like meshing your fingers together, where one set of fingers is the plates and one set of fingers is the dielectric. And it's much more difficult to make a high value capacitor with a ceramic, because ceramic's not got as higher permittivity, and because the plate area is not as large. But altogether, C1, C2, C3 make a wideband efficient coupling for AC signals and blocking for DC signals. If we look at the voltage on the drain, we can work out what it should be. It will be 5 milliamps times 50 ohms, all taken away from plus 15. If you don't fancy doing that in your head, you can put data label in. It's 14.75 effectively. So we need to block that because the network analyzer will not be very happy with us for putting the 15 volts, more or less, into its input. It's only interested in signals because it's meant to measure linear time invariant systems only. So we're expecting AC signals going in, we're expecting AC signals coming out. As it is, we will have AC signals going in and AC and DC coming out. While I'm a big fan of Australian rock bands, it's better if we block the DC. If you don't, network analyzer will probably trip at input, or in the simplest possible case, a little fuse will go inside and you either have to reset it by pushing a button or physically remove if it's a non-resetting fuse, remove it and replace it. Most of them have some sort of relay that opens and it says channel A tripped, and you have to go in and press a button, and oftentimes it beeps as well to let everybody in the laboratory know that you've buggered it up. So that's the overall setup. We can have a little look at the DC conditions, which we've done already. We can have a look at AC conditions and the transient as well. So AC will give us a Bode plot, and the transient will give us time domain. So x-axis for AC is in hertz is frequency, and x-axis for transient is the time in seconds. So I can go in the simulation, edit the simulation command. There's nothing there, damn. I right click that then, a bit easier. Delete that semicolon, so I've got .tran, start at 0, end at 3, start saving the data at the first millisecond. The little m is milli. If you want mega, it's big M, big E, big G. It's not big M. Spice doesn't care about upper or lower case. G is for giga. That could be small lowercase, that would be fine as well. So if you want 10 to the 6, it's MEG. Often trip people up. So I can simulate and run, and it will divide the screen in half, and I've got a graph pane with 2 milliseconds worth of data. That shouldn't be too surprising. I'm going to use a spacebar now to zoom in a bit. If you don't fancy that, you can also use Control Z, and I can zoom in with Control Z. If you want to zoom out a bit but not see the whole thing, Control B will take you back, and a spacebar will make it the side of the screen. When I install LTSpice, by the way, it's installed in my Dropbox, so everything I do updates everywhere without me having to think about it. And because LTSpice doesn't go into the Windows registry at all, you don't have to worry about it on a certain machine. Also, if you're in the Diamond or somewhere like that and you don't have admin privileges on the machine, it should be possible for you to run it off a USB stick if you need to. Obviously, if you don't have admin privileges, you won't have your Dropbox or whatever. You might be able to run it at your Google Drive, which you're provided by the university, or you might not. I've never tried it. So we've got the window. When I installed, by the way, I changed all the colours. So if you've just installed it fresh, the background will be grey. There probably won't be any grids on. If you want the grids on or off, it's Control G. That's different from if you want a ground, which is just you press G for the ground, but Control G is the grid. And I make the background of the graph pane white, and I change the colour of the graph traces as well. Also, I make the lines thick. I'll show that in a bit. So let's have a look at the output, and we should see sine waves, I hope. Sure enough. And if I look at the input, I'm going to take the input as here. All this business is to do with making sure there's no back reflections. The voltage that actually goes into the circuit we care about, or the voltage that appears at the input of the circuit we care about, is what's across this termination, R6. So this is my input. Perhaps not so surprising they are out of phase with each other. If you follow the signal through, thinking about what's going to happen to it along the way, you can show yourself pretty quickly that it should be in anti-phase or 180 degrees. Phase shift if you prefer. And we've got input voltage is 120 millivolts peak to ground, and output voltage is about 90 millivolts peak to ground. So the output voltage is actually less than the input voltage, so the gain is less than 1. And this is voltage gain, of course. If I did divide VN005, if I divided VA, the output, by the input, which is VN005, it would give me a rather odd looking graph, and it wouldn't tell me what I wanted to know. We can get the gain by another method if you like later, but if you want to do it on here, the way you would do it is right click, add a graph, add a cursor, right click, add the other cursor, then you take them, I don't know, probably to the peak I should think. We'll try and find the top, it's probably there. If I look at the graph, this it will tell me. Where's number 1? I'm going to the bottom, aren't I? You would have to sit there and see which way the numbers change. So you divide one through by the other, the minus signs don't matter, and it would tell you whatever it is. I don't know. That's about 1/5 more, just over a fifth more than that. The gain's probably about 0.7 something, I should think. Can work it out the old-fashioned way. Good old Microsoft calculator. 93.133 divided by 124.99. Sure enough, it's just over 0.7. But that's not the game we care about. The reason we are measuring like this is because the network analyzer accepts a voltage, and we must therefore provide a voltage, and it's expecting our transmission line that we plug into it, the BNC cable, to be 50 ohm terminated. So we must provide 50 ohm output impedance from our amplifier as well. As it is, what we actually care about is the AC component of the current in R4, because we will connect some other circuitry on here which has to be driven by a current, and that may be a photodiode amplifier, or so you use it in a fibre optic communication system to receive a signal, or it may be ADC, which requires a current input, for example. They often, or not often, but many of them, some of them at least, do, because if they're in current mode, they have much wider bandwidth, usually, depending on how it's been designed. So there are lots of circuits where you want a current input to test it. If you want to test your trans impedance amplifier and your photodiode system, you might want to use some circuit like this. So I don't really want to use R4. I don't really care about the DC part, and I'm not interested in the 50 ohm output impedance. The only thing is I've got to make sure all those things happen in order that I can get the network analysis properly. Network analyzer, of course, will not show us the time domain graph, but if you hook up to a regular oscilloscope, you should see something very similar to that. So at the moment it looks like gain is less than 1. If I was to do the current in R4 and I delete VA, because VA is not very significant to me now, I just click the graph pane, and then I press F5 and I get a gold pair of scissors, which is for delete. You can't delete. Oh, you can. Ah, they changed that. Cool. That used to be really annoying. Glad they changed that. Now I've got output current, which is what I care about, and an input voltage. And if you were to divide the maximum, it looks like it's about 6.85 by about 120 millivolts. You can do E-3 if you want at this point, that's okay. That hasn't rendered it properly, but never mind. Divided by 120 millivolt. Ah, there's a mistake. Back we go. You must use this plus minus. We have 0.056 amps per volt. So for every volt input I got, I should get 0.056 or 56 milliamps out, effectively. It's usual to do this in milliamps per volt, but I did it in the base units just then. As far as current is concerned, it's in phase. The reason for that is as this increases, the current here, in R4, it makes the voltage drop across R4 bigger. Consequently, if we did 15 minus the increasing voltage drop across R4, the voltage from here to the ground is actually dropping, because this voltage across here plus this voltage here must add up to the plus 15. This one is getting bigger, this one must be getting smaller. That's why we end up with the phase reversal. This current gets bigger, this voltage gets smaller. Right, so I think we're good on the transient simulation, so I go to the AC simulation now. There is a menu that you can use to do this, but I'm happy to do it this way. If you want to get to it, click on the schematic, simulate, edit simulation command, and you can ask it for the various analyses. So if we look at the AC, I'd run this now. This is still DC conditions it's showing me on the operating point, but I've got a Bode plot now, and I've got thick lines. So if you go into tools and into control panel and into drafting options, you can ask, or you can set the pen thickness. I like it to be a bit thicker. It's too thin otherwise. So we have magnitude in dB and phase on this side. VN05 is the input, and V as IR4 is output. No surprises, we only got resistors here. Sure enough, everything's dead flat. The level is not 0 dB because the AC is a small number, and also because we have some resistive losses, but the phase is flat. If there was impedance mismatch here, it wouldn't show up on this graph. The reason for that is Spice doesn't know that this bit, and this bit are a transmission line. It thinks that these resistors are closely connected together by very infinitely, in fact, short wires of absolutely no resistance at all. Unless you explain to it that there are transmission lines, and those transmission lines have a capacitance per unit length and an inductance per unit length and a resistance per unit length and a conductance per unit length, it doesn't know about it, and it doesn't care. So it will only answer the questions you ask it. If you fail to ask it a sensible question, it's not going to give you an answer you expect or hope for. Anyway, we've got input is VN005. I'll tell you what, I just make it let's call it in. It's lazy, but quite common. If I resimulate now, VN05 is not this node anymore, it's somewhere else in the circuit, I don't know where. If I click that one, it's VN, and VN in the black is what it was before when it was VN05, but now VN05 is something else. So you must label your nodes and then do your analysis. If you do analysis, change your node names and look at your graph, it won't be representative anymore. You have to do it in a certain order. So I'm going to make this blue because it's a bit easy to see. I right click just then, by the way. I can divide one by the other quite happily now, so we'll do IR over VN. So I right click and I can put in the mathematical expression, and I will delete that one. So we've got minus 36 dB. This is measured in amps per volt at the moment, which you can call it ohms if you like, that's okay. If you want to see it in linear, you can right click and you can ask it for linear, log or whatever, and you can also ask, instead of having magnitude and phase, you can have real part and imaginary part. That's fine. Anyway, I'm not too worried about it, but if you want to know the value, it's saying 15 milliohms raised to the minus 1. In other words, that's in Siemens, which is another way of saying amps per volt. But that's by the by. Decibels, there we go. Wow, that's a low number. So I'm interested, I've got pole 0 here. So for those of you in 225, yay, pole 0 is great. Then we have a mid-band, which is the region of flat frequency and minimum phase shift. And then at some higher frequency we have a 3 dB point where we've got to roll off, and it looks like we've got, don't know how many dB per decade that is. This is not going to quite get to a decade, but if it did, it would be there-ish. That's minus 56. That's at minus 42-ish. So it looks like that's heading for 20 dB per decade, but it then bends back because there's a 0 here. And then it looks like another pole, because the old phase is going down for all the poles. You can see the phase starts to go back up a little bit just here. Not really up, but it starts to turn. It's not going quite steeply down. But that's by the by. So I want to know the 3 dB point. I right click and I take 2 of these and I put one in the mid band. Exact frequency doesn't matter, but oftentimes we use kilohertz. As long as it's in this flat bit, it's okay. And I'm just going to move this second one to the right until I measure up down here magnitude of minus 3 dB. So at the moment it's minus 101 milli-dB, which is obviously 0.1. So I keep going, more. Oh, nearly. Little more. I can use the cursor keys now to adjust it, and this is the 2 nearest data points. So I'll probably take that one, because it's the lower frequency and we are hoping for big bandwidth, so this is a conservative estimate. 67.6 megahertz. This is actually the difference between the two. The frequency we're at cursor 2 is 67.608, not 607. The reason for that is I dropped the first one at a kilohertz, and that's the reason for the 1K difference. So 67 is reasonable. I mean, if you want to test a 100 gigabit per second transimpedance amplifier for a undersea fibre, it's not going to do it because you need about 50 gig of bandwidth for that. But with this sort of circuitry, op-amps and so forth, you're never going to achieve that. Op-amp just doesn't have the gain bandwidth product to do it. If you wanted to work at, say, 10 megahertz, this would be pretty much fine. If you wanted to work at 20 megahertz, it will be okay. 30, probably. 40, maybe. Not much more than that. But there's a large region of usable bandwidth. So that's the sort of simulation I would be doing if I was designing something like this. We can look at the implementation now in Proteus as well. I will do that as a separate video.